Hello, everybody.
Hello, Professor.
A very interesting subject or topic today is about classifying random regression when y is a binary variable. When we have seen so far multiple linear regression, we assume that y is a continuous variable. Okay, so mathematically speaking, y belongs to R. Okay, but in some applications, business application or economics applications, the variable y is not continuous. It takes binary variables, for example, 1 or 0. For example, supposing we want to classify good customers versus bad customers, and so y we take value of 1 if the customer is a good one, 0 if he's not a good one. Or we want to predict stock price next move. For example, up will be for up moves, y will take a value of 1. For down moves, y will take a value of 0. So these are kind of applications where standard multiple linear regression analysis is no more appropriate. And we need to apply some advanced models which are nonlinear in nature, like discriminant analysis, logistic regression, and probit regression. So we have seen that y can be regressed on b0, beta 0 plus beta 1 x1 plus beta k xk plus an error term. Okay, so we discussed models for dealing with explanatory variables representing qualitative information like dummy variables. X can be continuous or can be a dummy variable or even a categorical variable. So X can be two kinds of variables: continuous, belonging to R, binary variable, meaning 1 or 0, or categorical variables, meaning that X is equal to 1 or 2 or 3 or 4. For example, 4 classes. So example used were employed and unemployed, male, female, educated, not educated, and so on. This kind of variable we have used for X. So the way this information was incorporated into the regression model was by using indicator variables. When we have seen y x can be dummy variable or taking different variables indicates a kind of state of X. Dummy variables can take values of 0, 1 and can be applied to multiple linear regression. Okay? This is the kind of explanatory variables we have seen. They can be continuous, binary, or categorical. Now let's look to an example where a bank is interested in determining whether certain borrowers are credit worthy, meaning that if this potential customer or borrower is risk-free or representing a kind of economic and financial risk. So the bank has a variety of quantitative information and also qualitative information about each potential borrower or clients, and would like to classify them, the customers, into two groups: group of qualifying customers and group of non-qualifying customers or candidates. So should loans be made to these potential customers? This is the question. Can we make these loans to these potential customers? The answer is that we need to define a regression model to be able to discriminate between qualifying customers or candidates and non-qualifying customers or candidates. Also, another example, an investment company trying to determine the likelihood or the probability that certain firms, okay, firms or investments will end up in bankruptcy. So the goal of the financial analyst or the data analyst is to be able to discriminate between risky companies and risky and non-risky companies to decide on which the portfolio manager will invest his or her money. So the investment company has imposes quantitative information on the firms and is considering to classify them into two categories: group of bankrupt companies and group of non-bankrupt companies. This can be solved by setting up a regression model, not a regular one we have seen so far, but a new one based on discrete analysis, probit model, or logistic regression. So in these two examples, the y is taken a kind of binary values. It's not a continuous variable, but binary variables. Another example, the director of personnel for a large corporation needs to know which group of new trainees will be successful in a position at the company. So by using some demographic information, the director of personnel wants to classify trainees into two groups: those who will succeed and those who will not succeed in the company. So this is very important to hire new personnel. Another example, a marketing department of a retail firm is interested in predicting whether people will buy new products within the next year. So the marketing department will have the results from surveys given to a sample of potential buyers and a quantitative score representing propensity to buy or likelihood to buy as a summary measure from these surveys. So the department wants to use the score to divide customers between real potential customers and not real or not or risky employees or buyers. So each of these examples represents a case in which certain observations like people, firms, which are y, or which represent the variable y, are to be divided into groups. In all this example, y is taking two values because it's a group of customers, a group of firms, a group of companies. And these groups can be classified into two groups. For example, firms that do not qualify for credit, firms that will and will not go bankrupt, people that will and will not be successful in new positions, and people who will and will not purchase a new product. So the goal is to try to pick up or to pick which of the two groups its observation will fall into based on available information, meaning based on available x's, we will ask the following question: will y belong to group 1 or will y belong to group 0, based on information on current x's or inputs? Any questions? So we adopt a similar approach for situations where the dependence variable of interest is qualitative in nature. For example, situations are examined where the task is not to try to determine whether items do or do not fall into a certain group. And the dependence variable used to represent this situation will be a variable that has either the value 1 if the item is in the group, or the value 0 if the item is not in the group. So standard linear regression analysis is not designed, is not appropriate to analyze a binary y. So when your dependence variable y is not continuous, it is binary or categorical, please do not use standard linear regression, multiple linear regression, because it is not appropriate to analyze the variable y, since y is taken only two values, 1 or 0, meaning that y belongs to group 1 or belonging to group 0. So in the standard regression, the dependence variable y was a variable that could be effectively modeled as continuous variable, meaning that standard linear regression or multiple linear regression applies only to y when y is continuous, can take real numbers, near real values. When y is taking binary values 1, 0, 1, 0, 1, 0, the standard linear regression, multiple regression, is no more appropriate to model y. For modeling, is no more appropriate for modeling and predicting, forecasting y. The assumptions of the standard regression model are designed for such a situation. Y is continuous. So basically, multiple linear regression analysis assumptions are designed for, are appropriate when y is continuous. If y is no more continuous, it's binary, those assumptions are no more valid and not applicable, okay, cannot be applied to the y, where y is binary variable. So when y is equal to 0 or 1, several problems occur under standard regression model. First, the conditional mean of y given x is different. So under, it can be shown that the mean of y given x is equal to p. When y is binary variable, the conditional mean of y given x is equal a kind of probability. A probability denoted p. P is probability that the observation belongs to indicated group, where p is equal to the probability of y is equal to 1. So for normal regression, for multiple linear regression, mu of y given x is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 2 x3, for example, plus beta k xk. This is where y is continuous. But when y is discontinuous, it is binary variable, the expected value or the mean of y given x is equal a probability. And this probability is equal to the probability of y is equal to 1. And by the way, probabilities should be between 0 and 1. But when the regression is estimated, there is nothing to guarantee that the predictions from the estimated regression equation fall between 0 and 1. If y is binary and you run the regression, multiple regression, there is no guarantee that this probability, this one, is equal to 0, is between 0 and 1. Because the x's are not forced to be between 0 and 1, or the outputs after having processed the x's cannot be between 0 and 1. So the actual predictions can vary considerably with values above of 1 or even values below of 0. In this case, we cannot have probabilities larger than 1 or negative probabilities. By definition, a probability is always between 0 and 1. And by running linear or multiple linear regression to estimate these probabilities is misleading, because you may get probabilities larger than 1 or probabilities less than 0, when probabilities by definitions should lie between 0 and 1, including 0 and 1. Any question? So certain assumptions of the regression model will be violated. First one, the error term is not normally distributed. If y is binary or categorical, and you use multiple integration to model y, which is a binary variable, the assumption of normality is violated. Second, the variance around the regression line is not constant, meaning that the variance of the errors is no more constant. You know that the expected variance of the errors is equal to sigma. But when y is binary, this expected value of variance of sigma is no more equal to sigma, but it is equal to sigma index t, where t is time scripts varying through time, meaning that sigma is also varying through time. The result is that the variance of the errors is not constant, it is variable. Okay? It varies with time, meaning that the variance of errors is no more homoscedastic, the variance is heteroscedastic. So these are two violations of the assumptions when you use a multiple integration to model y when y is a binary variable. So problems occurring with applied standard regression technique to situation where depends variable y is equal to 0, 1. This kind of problems that you can face are regarding non-normality verification, and and constant variance violated assumption is also violated. Solution: you can use discriminant analysis or logistic regression. These are two alternative tools that can be used to model y, where y is a binary variable. Any questions? So let's look at discriminant analysis. Now let y be the dependence variable, where b is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta k xk. And y is equal to 1 if the observation falls into the group of interest, for example, group of 1, a group of non-bank corrupt companies, and y is equal to 0 if the observation does not fall into the group of interest. Okay? And let's explore the variables x. Used to help predicting into which the two groups, each of the observations in the sample should be classified. So x is information to predict the class of y. If you do have information on x, you can get the corresponding class of y. Okay? So discriminant analysis assumes the following assumptions. First one, variation of explanatory variables is the same for each group. So the variation in x's is the same for each group. So variation in x's when y is equal to 1 is equal to variation in x's when y is equal to 0. This is very strong assumptions, which is not always satisfied in real applications. Second assumption, explanatory variables are assumed to be approximately normally distributed, meaning that x's are assumed to follow a normal distribution, which is also a very strong assumption under discriminant analysis framework. So if discriminant analysis is used when x's are not normally distributed, it is not guaranteed to be optimal in such cases and may not provide good results, meaning that the predictions of y, of classes of y, are very poor predictions, are wrong predictions, because of not efficient estimated coefficients. So this is more serious limitations of discriminant analysis because it is supposed to limit the kinds of variables that can be used as inputs to the discriminant analysis equation. So under discriminant analysis, let's assume we apply linear regression to the data and we estimate previous equation. So the estimated equation is the following: D is equal to B0 plus B1 x1 plus B2 x2 plus BK xk. And we call D a discriminant score. D is a discriminant score. So if D, now to use D, we need to define a kind of cutoff. The cutoff is always by default set to 0.5. So if D is less or equal to the cutoff, and the cutoff is the variable C, then you assign the observation to group 0. If the cutoff D is larger than C, then you assign the observation to group 1. And D is equal to B0 plus B1 x1 plus BK xk. So if you do have information on x's, you know the b's, you can get D. D will be automatically between 0 and 1. If D is less than the cutoff, then you assign the observation to group 0. If it is larger than cutoff, you assign the observation to group 1. However, it is not always guaranteed that the D will have value of more than less being 0, 1. It is not guaranteed that you will get D between 0 and 1. So the goal to classify future observations correctly. This is the goal behind linear discriminant analysis. Now, how to estimate the B's? Beta 0, beta 1, beta k. They should be computed such that the number of misclassified future observations is minimized. So to get the B's, we simply need to write down a minimization problem where the goal is to minimize the error of misclassification rates. Please do remember that under multiple regression analysis, we seek to minimize the sum of squared errors to get estimates of beta 0, beta 1, beta k. But under discriminant analysis, we seek to minimize the misclassification rates. So estimate the equation for the discriminant score, we get co-circulation using 0, 1 dependence variable. This is the algorithm. This algorithm used to run linear discriminants. First step is to estimate the equation, meaning that you estimate this equation. This is the first step. The second step, record the predicted or fitted values from the estimated equation. These are the discriminant scores D, meaning that replace X by its corresponding values, and you got multiply B1 and the B's plus B0, you got corresponding D's. So you will get a vector of the D's. So finally, you need to set a cutoff. Choose a value of C, which is a cutoff, in a way that the probability of misclassification for future observations is minimized. So the first step is estimating D. Second one is to set a cutoff to discriminate between two groups. And the third step is to choose, second step is to estimate these. Third step is to choose the most suitable C to discriminate between classes. Now, how to choose the cutoff C? So by choosing C halfway between the average discriminant scores for the two groups, this is the best way, is to calculate the average of the two groups and take the value of C as this average. Another way is to take to set the value of C to 0.5. 0.5 is halfway between 0 and 1. So this is LD procedure, how to calculate C. C is equal to D0 bar plus D1 bar, where D0 bar is average discriminant score for group 0, the average value of D for group 0, and D1 is the average value of D for group 1. So C is equal to average value of D for group 0 plus average value of D for group 1 over 2, you get the cutoff value of C. When this is applicable, when the sample sizes for group 1 and group 2 are comparable, are similar. But what happens if the two groups are not equivalent? The number of observations in the two groups are not equivalent, meaning that the groups are not balanced. If it is the case, then the cutoff is equal to N0 multiplied by D0 bar plus N1 multiplied by D1 over N0 plus N1, where N0 is the sample size for group plablet 0 and N1 is the sample size for the group plablet 1. This is an example, okay, showing scatter plots of test 1 versus test 2 for satisfactory and unsatisfactory employees. So the employees have undergone a test, and we to classify test results into two groups: a group of satisfactory results and group of unsatisfactory results. So we got the group of ones and group of zeros. We got the results corresponding to test 1 and the results corresponding to test 2. And we got also the scatter plots of the results. So by using SAS AG, we got the following results. So this is the linear discriminant function for group 0 and for group 1. For group 0, when when y is equal to 0, or when d is equal to 0, so the variable we got beta 0 is minus 2898. Beta 1 multiplied by test 1 is equal 5.1, and beta 2 is 1.97. Okay? We got a kind of confusing matrix showing classification of results. So we got 16 zeros are correctly classified as zeros, and we got 4 zeros wrongly classified as ones. For ones, we got 5 zeros classified as 1, and we got 18 ones classified as ones. We can get also the error rates for zeros. It is 0.20. Error rate for ones, it is 0.1. And we got the total error. Total error is 0.2087, meaning that the error rate of this model, discrete analysis, is equal to 20.7%. Following discrete analysis, we can get two equations: equation for group 0 and equation for group 1. So equation for group 1 is the following. Group 0 is equal minus 298 plus 5.2 test 1 plus 1.97 test 2. Test 2 or group 2, group 1, the equation is minus 35.1.61 plus beta 1, which is 5.68 test 1, plus 2, which is beta 2, which is equal to 0.10 multiplied by test 2. These are the two equations we can use to discriminate between two groups. Do you have equations before I start moving up, please? Okay. So in sample classification, these two equations are applied to each employee. So this is the equation for group 0, equation for group 1. And the employee is then classified into the group for which his or her score is the highest. For example, if his score is equal to 0.6, then this the employee will be classified into group 1. If the C, or the score C, is equal to 0.3, then this client will be classified into group 0. Out of sample classification, these equations can also be used to classify any future applicants. For example, administer the tests, record the test scores, and compute the values for each equation. Then the applicant is then assigned to the group for which the value from equation is the highest. Any question regarding this? Okay. Goodness of fits. Like for multiple linear regression, we have used R-square to evaluate the goodness of fit of the regression. So what really matters in discriminant analysis is how well discriminant equations can classify future observations. So the percentage of correctly classified observations given discriminant analysis outputs can be used as a tool to evaluate the performance of the regression, okay, or to evaluate the percentage will likely overstate the quality of future classifications. There are other methods to assess the quality of future classifications when using discriminant analysis. So one method is to split original sample into two parts. A part using for estimation of the B's, so we can subdivide the data into two groups. The first group is used to estimate the B's, beta 0, beta 1, beta 2, beta k, and second group for yes, and second group is used for prediction purpose. So the first sample from the original data set will be split into two groups: group of training of equation and group for testing of the equation. Training of the data, so X's will be grouped into first group to estimate the B0, B1, Bk. The test group is used to evaluate the accuracy of the equation, where the predictions, the calculated predictions, are close to real observations or not. And observations are the classes. So discriminant analysis, sorry. So we use estimation sample to determine discriminant equation, calculating D is equal D is equal to B0 plus B1, Bk, and so on. And then use discriminant equations to classify the items or the subjects into the validation sample. So the percentage of correct classifications in the validation sample, so training sample is used to estimate the B's, validation sample is used to check whether estimate B's are yielding to results which are close to reality or not, true observation or not. So the percentage of correct classifications in the validation sample should provide a better indication of how much discriminant analysis will perform on future observations. So after this has been done, the two samples can then be combined to compute the discriminant analysis function. What are the limits of discriminant analysis? Statistically speaking, it is known to be statistically valid when we can assume that the independent variables, x's, are normally distributed. To consider linear discriminant analysis valid, equation valid, you need to check whether or not x's are normally distributed. Also, you need to check whether or not variances of x's are constant across positive and negative groups. So if not the case, the assumption normality excludes many possible variables as experimental variables. You need to drop x's which are not normally distributed. Now imagine that all dropped x's are not normally distributed. Then you end up with a very limited discriminant analysis equation. So even though linear regression was used to perform discriminant analysis, this is not typically the method of choice. There are some other methods which are nonlinear and very powerful, can be used to discriminate between class 0 and class 1. So let's look to another example of techniques which is more suitable for binary data compared to regular regulation where y has been transformed. So logistic regression is another procedure for modeling y, where y is binary, dependent variable that does not depend on assumption that dependent variables are normally distributed. So under logistic regression, x's are not assumed to be normally distributed. Also, x's are not assumed to be uh, uh, to have a constant variance. And when y is equal to 0 or 1, mu of y given x is equal to the probability that the observation belongs to the indicated group. For example, mu of y given x is equal to p is equal to p of x. Sorry, is equal to p, the probability, where probability is equal y of 1. This is mu, this is average value of y given x. So probabilities must be between 0 and 1, and thus to model the conditional mean of y, a function that is restricted to lie between 0 and 1 must be used. So to force p be between 0 and 1, we need to force a specific equation such that the resultant probability is always between 0 and 1. So by definition, we got mu of y given x is equal to p, probability, and equal to probability of y is equal 1. So the function considered in logistic regression, is called logistic function. And this logistic function is equal to mu given y is equal to mu of y given x is equal over 1 minus 1 plus exponential of minus beta 0 plus beta 1 beta x1 plus beta 2 x2 plus beta 3 x3 plus beta k x1. This is the response function of the logistic regression. So phi of z, where z is equal to x. So if phi of z is equal to 1 over 1 plus exponential of minus z. So for if whatever is the x, y will be always between 0 and 1. The maximum is 1 and the limit is 0. Beta 0 beta 0 so for each input x, the corresponding value of y will be between 0 and 1. And this is what we want, because y is a class taking value of 1 or value of 0. So this is an example showing the results from multiple linear regression. When you use multiple linear regression to calculate y, the corresponding y can be less than 0 or above 1. And by definition, a probability is always between 0 and 1. And the only form where we can assure that the probability of y is between 0 and 1 is by using a logistic regression. And this logistic regression assures that y is equal to 0 or 1. So the value of y is between 0 and 1. And the form used for logistic regression is this one. By setting this as main equation for regression, this expression is equivalent to this one, exactly the same one. So by using logistic regression, define it as this quantity, you can assure that the probability of y equal to 1 is between 0 and 1. And this can be seen graphically in this figure where phi of zeta is always between 0 and 1. Whatever is zeta can belongs to R. So going from minus infinity to plus infinity, whatever is the value of zeta, the corresponding output phi of zeta is always between 0 and 1. This is the graphical illustration that whatever is x, y will always be between 0 and 1 when logistic regression model is adopted. If you employ a linear probability model, it is very risky. The probability of y will not be will longer be between 0 and 1. It can be above 1 or less than 0, which is a big mistake. Any question regarding this figure or regarding this formula? Yes, please. Okay. So whatever is the independent variable, the dependent variable will always have a value between 0 and 1. Applying a cutoff, a specific cutoff, for example, by default, all softwares by default apply a cutoff equal to 0.5. So by applying cutoff 0.5, the corresponding dependent variable will be classified as being to class, as being 0, belonging to class 0, or as being or having a value of 1, so belonging to class 1. So logistic regression, the function works well for model probabilities because it is restricted to be between 0 and 1. Whatever is x's are x's, the resulting y or resulting probability of y will always be between 0 and y. This is the beauty of using logistic regression. Another advantage of logistic regression is that it is nonlinear. It's nonlinear function and can approximate the nonlinear relationship between y and x's. So whenever the relationship between y and x's is discontinuous and is nonlinear, logistic regression is very appropriate tool or function to approximate such a relationship. The description of the solution process is more complicated than the least squares because it requires derivations with respect of probabilities, which is out of scope of this lecture. But similarly, when you to calculate the optimal B's under linear regression, we optimize it. We wrote a kind of minimization problem where sum of squares are minimized with respect to x's. In logistic regression framework, we minimize classification rate with respect of probabilities. Probability of y equal to 1 and probability of y is equal to 0. So statistical packages can minimize these functions automatically and give you the resulting functions, the resulting logistic function by maximizing the likelihood estimation, where the goal is to minimize the misclassification rates. So under logistic regression, there's a zeta statistic and associated p-value, and to apply a kind of hypothesis tests. So under the null hypothesis, beta 1 is equal to 0, beta 1 is different from 0. Like for multiple integration, we use the student t-test to check the null hypothesis. For logistic regression, we use zeta statistic to check the hypothesis. And you need to look at the p-value to accept or reject the known hypothesis. When using logistic regression, the goal is to analyze of the analysis is to classify observations into a particular group. So like for a discrete analysis, we run two equations, one equation for group 1 and one equation for group 0. So for logistic regression, some rule must be designed to help decide in which group each observation should be classified. This is by computing predicted values of probability of group membership. And we need to define a decision rule. This decision rule corresponds to a threshold C, a cutoff. So logistic regression classify observation into y equal to 0 group if predicted value is below the cutoff, y is equal to 1 group otherwise. So a cutoff of 0.5 is popular because it gives equal chances to both groups to have balanced observations. If you do remember well, for multiple linear regression, we have used multiple adjust R-square to evaluate the goodness of fit of the regression. For logistic regression, we use what we call Hasmer-Lemshow statistical tests. Under Hasmer-Lemshow tests, the null hypothesis is we have a good fit. And each alternative hypothesis, we do not have a good fit. And the decision rule is to look at the p-value. If the p-value of the test is less than 5%, then you reject the good fit hypothesis and you accept not good fit hypothesis. Otherwise, if the p-value is larger than 5%, then you accept the null hypothesis of good fit and reject the alternative hypothesis of not good fit. So this is a similar approach for evaluating the goodness of fit of regression when y is discontinuous, is binary, by using logistic regression. So this is the output from SAS AG. So we got the intercept. This is logistic regression output. We got the intercept equal to minus 56.1678. Beta 1 of multiplied by test 1. Beta 1 is 0.4833. Beta 2 is 0.1652. Okay? The intercept is significant. Beta 1 is also significant because beta 0 and beta 1 are both significant because their respective p-values are less than 5%. Beta 2 is not significant because the p-value is equal to 0.1055, which is larger than 5%. Now, to evaluate the goodness of fit of logistic regression, we need to look at Wald test. The Wald test p-value, Wald test is the test representing Hosmer tests. Hosmer tests. So Wald test is a global test to check whether beta 1 is equal to beta 2 is equal to 0. Okay? Alternative hypothesis, at least one of the B's is different from 0. So according to Wald tests, H0 is rejected. And at least one of the B's is significant. Why? Because the p-value of Wald test is equal to 0.005, less than 5%. So you reject the null hypothesis that all coefficients of regressors are equal to 0 and accept the alternative one that at least one of them is different from 0. Any question regarding this? It is very similar to multiple linear regression. Okay. So this is information regarding observations. Total number of observations is 43. So we got 20 observations from group 0 and 23 from group 1. We will go back later on. We will see AIC. This is Akaike information criterion. This is Schwartz information criterion, and this is -2 log likelihood information criterion. These three criterions are used to pick the best model. For example, running regression, logistic regression with 2 x's against running logistic regression with 4 x's. For example, a full sample logistic regression, reduced logistic regressions and a full logistic regression. So do remember, for multiple regressions, we use it to pick the best one. We use it just R squared. For logistic regression, we do not have just R squared, but we do have 3 metrics: Akaike information, Schwartz information, and Mars log likelihood L. So the best one is the one with the lowest metrics. If these metrics are very low, they represent the best model. There are kinds of performance metrics you need to know for evaluation of accuracy of the model. We call some metrics called as accuracy, sensitivity, and specificity. Accuracy is ability of the model to classify, to correctly classify all examples. Now look at this table. This table is called confusing matrix. Confusing matrix, we got positive tests against gold standard. So positive samples, when classified as positive, we call them true positive. Positive samples, when classified as negative samples, we call them false positive. Negative samples, when classified positive samples, we call them false negative. And negative samples, when we classified negative samples, we call them true negatives. So the model with the highest accuracy is the best one. And accuracy can be calculated as being true positive plus true negatives over true positive plus false positive plus true positive plus false negative. This is accuracy. And 1 minus accuracy gives you error rates. So error rate is equal to 1 minus accuracy. You can also calculate sensitivity and specificity. Sensitivity is the ability of logistic regression to correctly classify true positives. And specificity is the ability of the logistic regression to correctly classify true negatives. For example, if true positives are risky companies or bankrupt companies, then you need to look sensitivity. If true positives are bankrupt companies or risky companies, as data analysts or credit analysts, you need to look sensitivity metric. And the model showing the high sensitivity metric should be the best one. Okay? If so, and specificity is the ability of the model to correctly classify true negatives. If you are more interested in good classification of non-bankrupt companies, for example, true negatives, negative is not bankrupt, so true negatives, if you're interested more in good classification of true negatives, if you are looking for non-bankrupt companies, better for you to look at specificity metric. So a model with high specificity metric means that this model is capable to correctly detect non-risky companies. So use this model to build your portfolio of non-risky companies. Any question regarding this slide, please? Okay, this is an example, okay, with cutoff. The probability level is the cutoff, okay? Accuracy is true positive plus true negatives divided by all samples. And correct classification rate is equal to 79.1, okay? 79.1, this is the correct classification rate. Sensitivity is ability to correctly, sensitivity is the ability of logistic regression to detect true positives. It is equal to 78.3. And specificity, so this is 78.3. This is 78.3 ability of logistic regression to correctly detect positive samples. And this sensitivity, specificity, is equal to 80.8, which is 80%, is the ability of the model to correctly detect negative, true negatives, which are non-bankrupt companies. So by varying, the goal of showing you this slide is to know that by varying the cutoff, this is the cutoff goes from 0 to, the cutoff goes from 0 to 1. Midway is 0.5. For the midway, you got a correct classification rate of 79.1%. So by varying the cutoff, you got different correct classification rate, different sensitivity metrics, and different specificity values. So by varying cutoff, you get different performance metrics. By default, set the cutoff to 0.5. This is this is the default value also for all statistical packages. Any question regarding this, please? SAS-EG will gives you Hosmer-Lemshow goodness of fit of the regression model. So under Hosmer-Lemshow tests, the null hypothesis is H0 a good fit. H1 it's not a good fit. H0 the model is showing a good fit. H1 the model is not showing a good fit. Okay? The p-value of Hosmer-Lemshow is equal to 0.441 p-value. 0.4113 is larger than 5%, so the decision is to accept H0, meaning that this regression model is showing a good fit. Okay? It's showing a good fit. So to evaluate the goodness of fit of the logistic regression model, just look at the Hosmer-Lemshow p-value. In equation, so this is the plot of probabilities. Okay, the circles indicate observed probabilities or observed samples, and this solid line is showing the predicted values, and this dashed area is representing the confidence interval, the 95% confidence interval for group equal to 1. So as you see, by using a logistic function, we got odd probabilities between 0 and 1. Between 0 and 1. Another performance metric for logistic regression is by looking to a ROC curve. A ROC curve is a kind of plot showing how sensitivity metric varies with 1 minus specificity, or it's a plot of sensitivity against specificity. So for a good model, a ROC curve area, so SAS-EG with so a good model should have area under the ROC curve. ROC curve is this one, is this curve, delimited by the diagonal line. Delimited by diagonal line. The ROC curve area is always between 0 and 1. 0 indicates a bad model. If area under ROC curve is equal to 1, it means that the model is perfect. The area under the curve is the area between ROC curve, okay, and the diagonal line. So this is the area under the ROC curve. Sorry. So this is the area under the ROC curve. The area under the curve is always between 0 and 1. 0 indicates a very poor model, a bad model, and a value of 1 indicates a perfect model. Following this logistic regression, we get an area under the curve equal to 0.9315, meaning that the model is very good because 0.9315 is very close to 1. This is another metric that can be used besides accuracy, error rate, sensitivity, and specificity. So accuracy is showing global performance of the model. Error rate is simply 1 minus accuracy. Sensitivity is the performance of the model in good classification of positive samples. Specificity is the ability of the model in classifying negative samples. Area under the ROC curve is another metric showing a compromise between sensitivity and specificity, and a value of 1 indicates that the model is a very good one. You can also use a kind of probit model. The probit model can also be used instead of logistic regression. They are very similar. The difference is the notation of the function. So this is the notation of y equal 1 over 1 plus minus zeta. This is the equation for logistic regression, and this is the equation for the probit model, probabilistic model or probit model. The difference is that the probit model is using a normal distribution. Logistic model is using a logistic distribution. So if you believe that the data is normally distributed, then use probits. If you believe that the data is following a logistic distribution, then use logistic regression. Probits and logits are two models that can be performed by using SAS-AG. Parisa tonight will show you how to use logits and probits under SAS. So both logits and probits provides probabilities values between 0 and 1. Whatever is x, whether x is negative or positive, the corresponding probability value is always between 0 and 1. The difference is simply in the nature, okay, of the distribution. If x's are supposed or assumed to follow a normal distribution, so use probits. If this is the probits, if you assume that the data follow normal distribution, then use probits. So this is probits. This is probits. So this is the probits. If you assume the data follow a normal distribution, use the probits. But if you believe that the data follow a logistic distribution, then use the logistic distribution. Okay, this is the difference between the two models. So let's do a recapitulation regarding linear probability model. If you use a linear probability model, the corresponding y or probability of y will be somewhere below 0 or above 1, which is not good. But if you use logits or probit model, the probability will always be between 0 and 1. Okay, so the beauty of using logits or probit is that the corresponding probability of y equal to 1 is always between 0 and 1. Cannot be above 1, cannot be below 0. But if you do use linear probability model, you will end up with some probabilities between 0 and 1, but also with some probabilities below 0 and probabilities above 1, which is not appropriate. So how to decide between logits and probits? simply by looking to the distribution of your data. If your data follow a normal distribution, use probits. If following a logistic distribution, then use logistic regression. So under OLS, we minimize it sum of squared errors under OLS. Under logits and probits, we minimize this quantity, where this phi is a nonlinear function. This is the phi. So under logits and probits, we minimize the errors, and the errors inside the expression we got this function phi. This is the key function to estimate logits and probits, and this function can be either a normal logistic, okay, logit, or can be a probit. Can be a probit. So under OLS, we minimize its mean of squared errors. Okay. The difference, it's very similar to logits and probits, but the difference is we incorporate this function psi or phi. This function phi. And this function phi is a nonlinear function used to force the probabilities of y equal to 1 between 0 and 1. Phi can take two forms of expressions: a normal distribution, a logistic distribution, or a normal distribution. Okay? Any question regarding this? And as data analyst, your role is to pick the best one. Before taking them, you may look at distribution of your data. If it follow normal distribution, then use probits. If it is following a logistic distribution, then pick logistic. Or if you don't know, simply run both of them. Run logistic regression, run probit regression, and the best one will be the one that maximizes accuracy. The best one that minimizes error rates. The best one will be the one that maximizes AUC. Okay? So we get results from logistic regression. So this is logistic, and this is probits. This is probits. So for the logistic regression, we get this. So beta 0 and beta 1 significant, beta 2 not significant. Okay? For the probits, we got intercept and beta 1 significant and beta 2 not significant. Okay? How to choose between them? The best model should have the lowest so the best one should have the lowest Akaike, lowest Schwarz, lowest -2 log likelihood. So the two models have similar Akaike, have similar Schwarz, and have similar -2 log likelihood. Okay? The two models. The two models are significant. The two models are significant because would p-value is less than 5%, meaning that the model is significant. Also for that one, the p-value is equal to 0.018, less than 5% means that the model is significant. Now we need to pick the best one. Let's look at Akaike, Schwarz, and -2 log Rayco-Hood. Look at intercept and covariates. Intercept and covariates mean that the model with intercepts and x1, x2. So we need to look at this information. So we need to, the best one is the one with the lowest values. 33,918 versus 33,316. So in terms of Akaike, probit is good. Probit is good. In terms of Schwarz, we got 38,644, 39,202, 202. So in terms of Schwarz, probit is good. Now let's look at -2 log likelihood. Logistic regression showing 27.918. Probit showing 27.36. So this one is good. So finally, probit model is the best one because it has the lowest Akaike, lowest Schwarz, lowest -2 log likelihood. So if you want to pick the best model, look at accuracy, look at this estimation methods, tools, and look at performance metrics. Now let's look at area under the curve. Area under the curve, we got 93.15 for probits. We got 93.15 for logistic regression. So both models are showing similar ROC curve. Okay. In terms of goodness of fits, H0 good fits, H1 not good fits, and the p-value is 0.45, larger than 5%, so except H0. So good fits, this is a good fit. Good fit is okay. For this one, 41 probability is 41.13. It's a good fit also. It's also a good fit. Any question regarding this? So the lecture is over. If you do have a question, please ask me.
Sir, last week you said you're gonna give us feedback for the project. Are you gonna post that?
Yes, I will post them, yes.
So through Moodle?
On Moodle, yes.
Okay, thank you.
Thank you.
Thank you.
Thank you. Other questions?
If we have question on the project, are we gonna have to make appointment with you?
Yes, send me an email and we meet on Zoom, private meeting.
Okay, thank you.
Thank you very much. Other questions? Okay, so please do not forget to meet with Parisa for the tutorial and see you next week. Thank you very much and have a good night. Thank you.